This is Andrey Belenko from Forensics in Moscow. He presented here in Bergen in December 2010 at the very first Passwords conference.
The only guy who ever wore a tie to these.
Yeah, and we have to tell the story once again. Right on, mate?
Go ahead.
Look at yourselves. What you look like. And he had the first talk on the second day of the conference. And on day one, he was dressed like a normal person. And on the second day, he came in a suit and white shirt and tie and was like, are you the guy going to talk about GPU cracking? But he looked really handsome. I'll give him that. But. Okay, so no further ado, this is Andrey Belenko, and I would just say he needs a warm welcome, being back in Bergen again.
Thank you very much. Yeah, one small correction. VF Forensics is in Chicago, but yeah, I still work from Moscow. Today I would like to tell you a little bit about iCloud Keychain and changes to data protection in iOS 7. So let's start with the shorter and simpler part with the data protection. As some of you might know, data protection is a set of technologies in iOS operating system that are designed to protect user data from unauthorized access. Those technologies include several different mechanisms. One of them, and very important one, is the keychain. Keychain is a storage of passwords, basically. It's a central storage of passwords, and iOS manages that storage. Keychain was there in iPhone since the very beginning, since the very first iPhone, but before iOS 4, it was, well, not very good. The encryption key that was used to protect passwords was fixed for a particular device. So every device, well, speaking in a way, every device came with the hard-coded key that was protecting the keychain. And no matter how many times you reset or wipe your device, the key remained the same. So obviously that was no good. But fortunately, starting with iOS 4 and going forward, Apple redesigned the keychain encryption completely. It was now using random per item key, and that key was in turn protected with another key that was based on desired item accessibility. And what exactly is item accessibility? Well, it is basically, it's hard to explain. Well, some applications need to access keychain items when they're running, when the device is unlocked. Other device might need to access keychain items when the device is locked. Well, think about this. If you're designing, for example, a browser, and you're adding feature like autocomplete for passwords or something like that, it is very likely that browser will only need to access stored passwords only when device is unlocked. So there is no way user will browse the internet while device is locked, right? So you can specify that this keychain item must be protected with the, must be accessible only when the device is unlocked. On the other hand, if you're designing something like email application, that application might want to access the stored password even when the device is locked. For example, if application is fetching mail in background, this must be specified that application wants to access password even when device is locked. And this is what item accessibility is. iOS 5 modified keychain encryption a little bit. First of all, it switched from AES-CBC mode to GCM, Galois counter mode, which is authenticated encryption, which is a very good step. Encryption keys remained also per item random keys, but another major improvement was that beginning with iOS 5, not only passwords themselves, but also all the metadata associated with the keychain item, such as login name, server name, creation date, modification date, whatever. This stuff was also encrypted. So beginning with iOS 5, all metadata is also encrypted. And you may ask, how Apple performs the search on the keychain? Well, in addition, well, before that, they stored the metadata in plain text, and password was encrypted. Now, everything is encrypted, but they store the SHA-1 hash of metadata items in the database. So instead of storing, for example, creation date, they store hash of the creation date. Instead of storing username, they store hash of the username. This way, application can still perform some queries on keychain to look up the items. Another major component of data protection is storage encryption. It was introduced in iOS 4. Well, some think that it was introduced before, but I would say that before iOS 4, encryption was there merely to facilitate fast device wipe. It was not designed to provide any sort of confidentiality. But beginning with iOS 4, encryption was implemented properly. It is a file-level encryption. In that sense, it is very much like Microsoft Windows encrypted file system. It's not like PGP whole disk encryption or Linux dmcrypt or other block encryption things. And this is why carving for deleted files is nearly impossible on Apple devices. Encryption is done very similar to keychain item encryption. Every file is encrypted with a random key, and that key is in turn encrypted with a protection key based on protection class. Protection class is the same as accessibility class for keychain items. With iOS 4, we had only two such classes, file protection none, which meant that the file is encrypted but can be accessed at all times, even if device is locked, and file protection complete. And files protected with this one could be opened only when device is unlocked. And that is not only some check if device is locked, then don't allow this file to be opened. This was enforced and disenforced cryptographically. So if device is locked, there is just no encryption key that could decrypt that file. iOS 5 added two new classes. One, complete until first user authentication, which prevented access to the file until user has unlocked the device at least once. And once device is unlocked, that file remained accessible until the device is powered off or rebooted. And the second new one was complete unless open. That one is very interesting. It is based on public key crypto. Specifically, it uses Daniel Bernstein's curve 25519. And what that class does is that you can create a file and open it, for creation at any time, even if device is locked, and you can write to it. But once you close the file handle, you can only open that file if the device is unlocked. So this is very useful for things like receiving email in background, taking pictures without unlocking the device, and so on. So what's new with iOS 7? Well, with the encryption stuff, the storage encryption, I haven't seen anything noticeable. Existing tools continue to work, and they don't seem to screw things up. So everything works, everything decrypts, and everybody's happy. There is one thing. Apple is encouraging developers to use protection classes because, well, protection classes have been introduced back in iOS 4 times, which is like 3 years ago, but adoption among developers was very, very low. So nobody cares about this. Nobody uses that because this is like a lot of brain damage. So how Apple approaches this problem? Well, typical Apple manner. Now, by default, everything is encrypted with the most restrictive protection class. So if you want your your application not to crash, well, you have to figure out why it crashes and change the protection class and whatever. And this is actually a serious problem. So I faced a crash because of that. My application was writing to a log file, text log. Application is writing to logs all the time. And that application was also performing some tasks in background. On the development device, everything was fine, everything works, nothing crashes. Ooh, let's push to production. Let's push to production, first test, crash. Why? Because the production devices has passcodes. When device is locked, after 10 seconds after the device is locked, encryption keys are removed from the memory, and all the file handles become unwritable. So we have a crash. So yeah, thank you, Apple, for forcing the encryption. And that was not even my code. That was an open source library for writing logs. So it was actually a problem inside that source code of that library. Well, keychain. Keychain format has changed a little bit. So encryption hasn't changed, but the encoding of data and metadata has changed. Before that, Apple has used binary property list encoding, and now they're using ASN.1, which is interesting. Well, you don't really see Apple switching from something proprietary to something standard every day. So the question which I had is, why are they doing this? So I don't know the answer, the definite answer, but here are three speculations on the point. First, and probably the most important one, that ASN.1 basic encoding rules or distinguished encoding rules, they are sequential. So you can actually receive the stream and parse it as it arrives. With binary property list, you actually have to receive all the data because the table of contents located at the end of the stream. This is one advantage. The second one is the ASN.1 is more compact, and it is cross-platform. So this may be a hint that keychain is coming to Windows, or I don't know, maybe, maybe not. So that's it about data protection, and now let's move to iCloud Keychain. Well, iCloud Keychain was arguably one of the most hyped features. It was presented at WWDC back in June, but unfortunately, some other revelations by Snowden, they came at about the same time, and so Apple became much less vocal about this feature, and they actually introduced it with the feature was present in all iOS 7 betas. It was not present in iOS 7 release, and it was reintroduced only with the release of OS 10 Mavericks in October. So let's talk about this in a little more detail. So why do this? Well, first of all, I have to say that this is not this is really my 20% project at work. So it's not something I put a lot of effort into, but still, yeah. The motivation was this. So Apple makes a lot of claims about the security. So they state that information is encrypted and cannot be read by Apple. And more interestingly, Apple can't access any of the key material that could be used to decrypt that data. So I think it's natural desire to know whether this is true or not. So let's, and it's not only about Apple, you know, because there are others who may force Apple to reveal some information. And I'm not saying that Apple wants to read my data, but what I merely want to know is, do they have the technical possibility to hand over my data in any decryptable or whatever form? Yeah, take your pictures. So let's get back to iCloud. Well, iCloud is it's not one service. It's a set of many services. As you can see, this is just screen you can see on your iPhone when you can enable, disable different services. And on the left, you can see the associated configuration, part of the configuration file, which is unique for every account. So Apple has technical ability to restrict set of keychain services for a particular account, but that's not the point. The point of this slide is that there are many services that go by the name of iCloud. And today we will look only on two of them that are used by Keychain, by iCloud Keychain. Those are Keychain Sync and Key Value. So the first question, when you want to analyze something, the first question is, where do you look? So you don't have to look too hard because the very same configuration file contains the endpoints, the server names for the services we're interested in. And specifically, you can see the URLs of those services. So they are standard, and this P19, so they start with some random number, which is not really random, it's sequential. So as more people register for Apple IDs, I think that Apple adds servers or names, and so this is kind of poor man's load balancing. So now we have this knowledge, and we want to figure out what exactly gets sent to those services. So we take the device, set up the iCloud keychain, and just sniff the traffic to figure out what's happening. So it is very easy to see that keychain and keybag are sent to the key value service, and something secret, something very secret, is sent to escrow proxy, which is the keychain sync service, and this is key value service. Few words about terminology. Keychain is your passwords, and keybag is a set of keys that are used to encrypt the keychain, the password inside your keychain. So this is Apple terminology, so I'm just trying to explain it as simple as possible. Keybag is a set of keys that encrypt keychain, and keychain is just a set of passwords. And how exactly do we know this? Well, it's not very hard, because although everything is inside HTTPS, there is no certificate pinning, so you just import your certificate, set up proxy, and you see all the data in clear. Wow. Now let's try to figure out what exactly happens with this in more detail, because this is obviously not detailed enough. We want to know more. When you set up an iCloud keychain, you actually have a number of options. The default is simple iCloud security code, 4 digits. Let's see how it works. What happens when you enable this? First of all, a random password is generated on the device. It looks like this. So it is 24 random numbers, random characters. The next thing that happens on the device is that a new keybag is generated, and passwords from the keychain that are marked as exportable, as the ones that can be uploaded to the iCloud keychain, are encrypted with this new keybag using AES Galore counter mode. Then this random password is used to protect that generated keybag. So essentially, this random password becomes a master password for your keychain entries. This is what this diagram says. This stuff is then uploaded to key value service. Not the password, only the encrypted stuff. So this is more or less okay. But what is missing from this picture is iCloud security code. There is no on this picture. So let's try to find out what's happening to it. So when you enter iCloud security code, it is fed through PBKDF2 with 10,000 iterations, and that key is used to encrypt random password. And encrypted random password is sent to escrow proxy. So now we have more or less the overall architecture of the iCloud keychain thing. Now let's see at what exactly is stored in the key value service. Well, first of all, let me state that this service is not new at all. It was probably the first iCloud service introduced, and a lot of applications are using it to keep preferences in sync across devices. One of the examples is, for example, Safari uses this service to sync your opened tabs on different devices. So it's not something exclusive to iCloud Keychain. But iCloud Keychain uses these two stores. And what is interesting about those stores is that you can see that it says Cloud Keychain Proxy 3. And during iOS 7 beta, it was just Cloud Keychain proxy. So apparently there's been some development and some last-minute changes to the system. Same with secure backup daemon. So apparently Apple been changing something. And during beta, they have purged those stores several times for all accounts. Those are the keys and description of the values that are uploaded to the iCloud as part of iCloud keychain. So probably the most important one is this one, which contains metadata such as iCloud security code complexity. So it's basically a flag which tells you whether the security code is simple 4 digits or something more complex. Timestamp and country. This shows whether the escrow service is used or not. We will get to this later. This is the keyback. Keyback is encrypted with a master password, and you see there is no indication of master password. As we figured out earlier, master password is sent to escrow proxy. And what exactly is escrow proxy? Well, this is a new service. And my guess is that it was designed exclusively for iCloud keychain, but is actually more generic. It can store any number of secret data, any number of secret items. Access to the service requires authentication token, and this is how all iCloud services work. So you need to know Apple ID and Apple ID password. Using that, you authenticate to iCloud, and in return you get your number, account number, and authentication token. And using that token and number, you talk to all the services. This is the case with this proxy, with this service. You need the same token to access the service, but to actually get data, to read data that was sent to the service, you need additional level of authentication. You need to receive an SMS challenge, and you need to complete a secure remote password authentication, SRP authentication. The fun fact about this service is that user agent that runs on iOS and OS X is called Lucky2. And if you Google that, you will find out that Lucky2 is a character from Mario Brothers Nintendo game, which is the cloud. So apparently there are some huge Nintendo fans in Apple in California, and I have no idea what, like iCloud, maybe there is some sort of like cloud, like YouTube, whatever. So the heart of the escrow proxy, as you can see here, is this secure remote password. What is it exactly? Secure remote password is a protocol designed by Stanford University, which is a zero-knowledge password-proof scheme. And I'm not sure if, probably some of you are familiar with this. If I'm not mistaken, one of the leaks from Blizzard, perhaps, they have been using this I think. So it's not new, but actually, I would say that this is probably the most large-scale deployment of secure remote password in mass industries, because Blizzard was big, but Apple probably bigger. What's the point of this protocol? Well, it was designed with 2 goals in mind. First, be free of any patents, so there are no patents covering SRP. And second, security, specifically attacker that can sniff traffic or can meet traffic cannot deduce enough information to perform offline attack on the password. So even if you have a man-in-the-middle condition on the running SRP, you cannot get like challenge response or something. You cannot get enough data to then mount an offline brute force attack. When implemented correctly, SRP will only allow attacker 1 password guess per connection. So attacker connects to the server, guesses 1 password, tries to guess 1 password. If the password is not correct, the server will drop the connection. So reconnect. This enables like relatively easy throttling of the password attempts. Another thing is that password verifier is not sufficient for impersonation. This means that if server storage gets compromised, for example, if somebody gets hold of all the hashes, which are called password verifiers, of all password verifiers from Apple, they will not be able to use those password verifiers directly to impersonate you, to impersonate as a user. They will have to first run through a brute force to recover the original passwords. And escrow proxy uses a latest version, latest flavor of this protocol, which is SRP6A. So this is how the protocol works. It consists of two main phases. And before the protocol can start, the parties have to agree upon some of the parameters. So they need to select hash function, they need to select group, and they need to select multiplier k, which is, well, in this case, in case of SRP6A, it is a hash of group parameters. The password verifier is the thing which is stored on the server. It consists of the salt, which is random, and value v, which is generator to the raised to the power x computed from salt and user password. So the protocol itself runs as follows. So the device initiates the protocol. It generates a random number a, raises generator to the power of a, and sends that a capital along with the user ID to the server. Server generates random number b, computes this value, and sends it back to the device. Now, both the server and the device perform some mathematical operations that result in the value key. Key here is the shared encryption key. It is the same for both the device and the server. But to be absolutely certain about this, both parties need to ensure that they actually agreed on the same key. They need to make sure that the key is the same on both ends. This is done during key verification phase, and it's done this way. Both parties compute M, and then device sends M to the server. Server verifies that M is correct, and if it's not, and it is very important, that server must drop the connection if M is not correct. And also, it is also very important that device must present its proof, M, first, not the server. So in this sense, everything is implemented correctly. Escrow proxy implements very standard SRP. It's very by the book. So you can open the specification and you can see that everything is just exactly as it's written in specification. There are only few minor changes. Well, first of all, the hash function is SHA-256. The group is 2048-bit group specified in RFC 5054, which is an RFC for SRP authentication in TLS. And the protocol itself is modified to accept SMS challenge codes. So not only random number and user ID is sent, but also a SMS challenge, which is sent by the server to the user's phone. So this is how the protocol works, but how the exact process works. So when the device wants to recover some data from the escrow proxy, it first lists the available escrow records. So it issues get records command to the server, and server responds with the list of available records. Then device asks for the list of associated phone numbers. So it runs get SMS targets command, and the server responds with a list of phone numbers that are associated with an account. I'd like to say that those phone numbers are used only for display purposes. So the device will show you notification something like, we have sent you an SMS to number blah blah blah. Please enter the SMS code. So device will not send this number back. It will not let user to select the phone number to send a challenge to. So next, the device requests that SMS challenge to be sent. And once user enters that SMS challenge into the device, it initiates the SRP protocol. So SRP init command, it accepts the DSID. DSID is a numeric identifier of your Apple ID, which is probably directory services ID or something. A is the random number, SMS code is the SMS challenge, and the server responds with the unique ID of the transaction with the same DSID, with random salt, well, salt associated with an account, and random value B. And after that, device requests the actual recover of the data. So it computes value M, which is most important piece of information here. And if M is correct, server will send back IV and encrypted escrowed record. And that escrow record is encrypted with the key K, which is a shared key computed during the SRP authentication. So probably this is too much, but yeah, just bear with me for a second. So I will try to explain this in more detail. So what other commands are available for this service? Well, the very first thing the device does when you enable iCloud Keychain is to run getclub cert command. I'm not sure what it's doing. Probably it gets some certificate or whatever. I don't know. I haven't seen it used too much. And roll sends secret data to the service for storage. Get records, get SMS targets, generate SMS challenge, SRP init, recover, we have just covered. The last one is funny. Alter SMS target. It enables you to change the phone number to which the SMS will be sent. This is not exposed anywhere in the UI, but I have a Python script that can do this. So this actually leads me to believe that this SMS has nothing to do with two-factor authentication at all. So this might be, well, some sort of rate limiting or whatever. I don't know, but yeah, one difference. This thing, the only difference from other commands is that it requires you to supply Apple ID and password. It will not work if you supply authentication token. So, but yet, if you know Apple ID and password, you can choose any number you want. So you don't have to worry about this.
So it falls apart.
It's not falling apart. I just don't think it's a two-factor authentication in the sense that we used to. So it may be a two-factor authentication to combat a situation where somebody intercepted your authentication token. But yeah, honestly, I think this is very, very strange. And also, and Apple states this on their website, this SMS thing, it doesn't work in some countries. Probably they don't have the global SMS coverage or something. So most countries do work. Norway works, Russia works, but some don't. And yeah, again, presence of this thing makes me think that this is not exactly a two-factor authentication we're used to. So, well, okay, let's get back to our escrow record. Look at this and try to figure out what exactly we can get from this server. Well, I can help you. We will get a scroll record, which is random password encrypted with the key computed from the iCloud security code. And our goal is to somehow decrypt the passwords that are sent to the iCloud from the keychain. And to decrypt the keychain, we need to get random password. And to get random password, we need apparently to get the key. And to get the key, we need to get iCloud security code. So how do we do this? Well, apparently, this stuff is stored by Apple on their servers. iCloud security code is 4 digits by default. Anybody sees any problem? And Apple states that information cannot be read by Apple. Really? Really? Well, my response is that yes, they can. And here's how. If you're Apple or anybody with similar level of access, you can get data, and you can run offline guessing on the iCloud security code. Since there are only 10,000 possible simple security codes, the attack will be almost instant and always successful. With iCloud security code, you can decrypt keyback password, sorry. Keyback password will decrypt the keyback keys. And with unlocked keyback, you can decrypt all the keychain items that are synced to the iCloud. So Apple or any other adversary with similar level of access to their storage can near instantly decrypt master password and all iCloud keychain records for default settings. So apparently, this is, I think this is important to know. Okay, but what about other setup options? So far we have only looked at the default, but yet I think everybody here understands that default cannot be secure. So what about others? Well, use a complex security code. Well, diagram is exactly the same, except that instead of the simple 4-digit, we can use arbitrarily long passphrase or password. So everything is exactly the same. Offline password recovery is still possible, but it won't be as successful because there are much more possible passwords, and it will not be like guaranteed to succeed. The passwords are apparently more complex, but again, attack is still possible because we have data stored in the escrow service. Get random security code. This is the third option. So how this works exactly? Well, this part is not used. If you choose to use random password as a master password for your iCloud keychain, then this part shown in red will not be used, and the whole diagram will look only like this. So escrow proxy is not used at all, and probably random security code is saved somewhere in the device. Well, for device to be able to sync, it must be able to compute the key, and it must be able to somehow store either the random key, either the random password, or the encryption key. So, but actually I haven't verified this, but my guess is that they're storing something, and that might be extracted. So the last one is to not use security code at all, and this is a very interesting one. Unfortunately, I don't know how it works yet. What I can tell you about this is that it's not using escrow proxy. It is using key value service. It looks like it maintains some sort of key directory for all your devices, and they somehow communicate with each other through this service. But I'm not really sure how it works. So Apple claims that in this case, no passwords are uploaded to the iCloud keychain, and so far this seems to be the case. So it looks like devices are exchanging keys through the key value service, but actual password exchange happens through push messages or something. And yeah, this is work in progress. Maybe when I have more time, I will figure out how it works. So this is pretty much it. Conclusions for today are pretty much as usual. Trust your vendor, but verify the claims, even if the vendor is Apple. Never ever use simple iCloud security code. Do not think that SMS that you receive as a part of iCloud keychain DUNS has anything to do with two-factor authentication. It's not. It's for some other reason. I'm not sure exactly for which one. And yet I can say that iCloud keychain is reasonably well engineered, although it definitely has shortcomings. Why am I saying this? Well, we've been looking at this system from the point of view, can Apple compromise this? Well, definitely can, and there are many different ways Apple can access your data. But think about this from different perspective, can an outside attacker compromise this? And I would say that with respect to outside attacker, the system is reasonably well engineered because there are proper safeguards in place. Securing with password is a fair choice of protocol for this stuff. And yeah, they're definitely doing rate limiting and account locking if you try to brute force SMS challenge or iCloud security code. So I have my account locked for some time because of that. During iOS beta, the SMS challenges that you received, they were 4 digits. Now they're 6 digits, so Apple is constantly adjusting. So yeah, it's not perfect, but it's reasonably well, I would say. That's it. Thank you very much. If you have any questions, I will be happy to answer them.
Questions for Andrey?
You said that it's possible to get the data from Apple side, but what's the difficulty to get this online from user side? Is it possible to send pins to Apple and receive some information back that your pin wrong or data couldn't be restored or something like this?
The question is whether it's possible to mount an online attack. Yeah. Well, yeah. Just a second. I will. Say again. So back to this slide. To mount an online attack, you would probably focus on this guy. And to do this, you will basically need 2 things to be successful with this attack. You will need to know Apple ID and password of the user and iCloud security code. So let's assume that you know Apple ID and the password because, well, you just know it. You need to brute force or somehow recover the 4-digit PIN. Well, I would say that if you're not Apple, this is relatively difficult because trying each PIN requires you to run an SRP against the server. And the server will basically throttle you down after several attempts. And then, after like 10 attempts, it will just lock the account. So this is the safeguard. And also, you will have to receive SMS challenge for each one, for each attempt. And if you just try to send fake SMS challenges, fake data instead of proper SMS challenges, you also get your account locked. So the mechanism of account locking is not clear, but there are 2 sorts of account lockout. There is soft lock and hard lock. Soft lock happens pretty quickly. Hard lock happens if you ignore the soft lock and continue to do what you're doing. Like the normal tools, the phone will not be, well, it will honor the soft lock thing and will not allow you to do anything. But if you're, for example, using some automated scripts and ignore soft lock, then the account will go in hard lock, and then you have only to reset the stuff, reset the thing.
So it's also kind of DOS attack for remote user. If you know what email and password, then you could just somewhere iPhone remote.
Yeah, the comment is that this can constitute a denial of service attack. Yes, this can probably be the case. So it's fairly easy to lock user's account. But again, this lock is only, it's not the iCloud, the Apple account lock. It's only for this particular service. So user will not be able to recover his iCloud keychain. Yes, this is true.
My second question is about you said the first step that it is very easy to get certificate HTTP
The question is, the second question is about certificates, certificate pinning. You mean this?
Yes.
You don't, well, the communication between device and server happens over HTTPS. To intercept HTTPS, you have to be like, you have to mount a man-in-the-middle attack. So you basically place proxy server here. For this to be successful, you need the device to trust your proxy server. The device connects to the server, but actually it connects to your proxy, and device must verify that it's talking to proxy, to server, not to your proxy. So to achieve this, you generate absolutely any certificate. You save it to the device. You import it to your iPhone. You mark it as trusted, and after that, you just conduct man-in-the-middle. What I'm trying to say here is that this thing is not using certificate pinning. Certificate pinning is the thing when the program which talks to the server uses hard-coded certificate, and this thing is not using it. So it is easy to do a man-in-the-middle on this account. Apple.
It is easy to configure, but you would have to do a little bit of work to either social engineer somebody to install a certificate.
No, it's not about. It's not about. This is just a setup for research purposes. This is how I sniff the traffic. So it's not about tricking somebody to like running man-in-the-middle against somebody. It's a matter of fact of running man-in-the-middle against my own device just to figure out what happens. Because if the program, if the phone, for example, uses certificate pinning for talking to this thing would be much, much harder because you have to, and unless your device is jailbroken, it's almost impossible to do this.
So you are talking from a research perspective.
This is
where you own the device, not attacking somebody else's communication.
No, this is basically how to sniff, how to figure out what happens with the device, not how to attack somebody by using this technique. So, and Apple is making this pretty easy to figure out what happens, because no pinning. I mean, they use pinning for things like App Store and iTunes Store for like money-related services. They do, but for other services, most of their cloud stuff, no pinning. More questions?
To this one, it's like not like vulnerability of Apple things, because in this case, a device shouldn't connect at all to server, because this certificate is not corresponding to exact server. This is like a problem from Apple side.
Yeah, absolutely. This is a problem, and this is why it is in red.
Yes, because if you couldn't get this information, you couldn't analyze everything else after that.
You can, if there is pinning, there are ways around it, but it's just harder because you need to get the binary, patch the checks, do a lot of boring stuff. So actually, lack of pinning, well, if you ask me from a like security researcher point of view, lack of pinning, lack of certificate pinning is always on the reports if you do like application assessment. If application is not doing certificate pinning, you always put it into report and say that this is like high priority or medium priority, high risk or something, depending on the application. But it is always an issue, and there are reasons not to do it. But I think for stuff like this, they definitely should do it because this is important.
More questions?
Thank you very much.
Yeah.
Break.